let me look at MS and NP. M in series first and then N in parallel. As I told you, this configuration is not preferred configuration. This is what it shows. You first put 14 or what M cells in series, you put another M cell in series, and this you call it a string. Each one of them is a string, and then you put multiple strings in parallel, and that gives you the N strings in parallel. It will give you MSNP. 14 cells, if you connect it in series, it will give you 48 volt. So, it becomes 48 volt. If you put 20 cells in series, it will give you close to 72 volts. So, that is how the battery packs are designed. Of course, as I told you, this is not the best way. We will come to that in a few minutes. 100 cells in series will give you 365 volt, 200 cells in series will give you 730 volt battery. Strings can be connected in parallel to increase capacity. So, if I use 14S into 2P or 15S cell, I get 48 volt, because 14 series means 48 volt into 2 in parallel, each is 14Ah, 15Ah capacity. So, I get, you multiply this 96 into 15 ampere hour, it is 1.5 kilowatt hour capacity. Any capacity can be built, any voltage, any current can be built using something like that. But there is a concern. I put 14 of them in series. Let us say cells at slightly different voltage at any time during charging or discharging. Suppose the voltage of these together works out to be at any time 51 volt, and for this it works to 49.5 volt. What will happen? String voltage of the two strings are different, and you connect them in parallel. Immediately a current will start flowing like this, because the voltage has to be same. This is internal current, not external. This is called balancing. And every time you charge or discharge, the voltages of number of cells in series will not be same. So, a lot of balancing will be required. A lot of these balancing actually hurts. You are actually discharging and charging the cells. The cell life goes down, pack life goes down. Unless cells are exactly the same voltage. Even if you take the cells at the time of manufacturing, measure, if they are exactly the same, after some usage, as SOH becomes from 100% to 99%, the voltage will not remain same, and the current will keep on flowing from one string to another. This will happen continuously while charging and discharging. Even when idle, you will keep on trying to balance, and not good for battery. So, this mechanism MSNP is not used. What is used is something like this. You first create a module. This is a module. Put N series cells in parallel, and then you connect them. So, this is a module, this is a module. First you connect the module, and then you put module into series. If you put 4 cells in parallel of 15Ah, you get 60Ah. 8 will give you 120Ah, 16 will give you 240Ah. So, you get a module of different Ah. Now, you connect them in series to make battery of higher voltage. If you put 14 modules of 60Ah, you will get 4P, 14S, 51 volt, 60 ampere hour. Capacity is 3.06. If we connect 14 modules of 120 ampere hour, In series you will get 8p14s or 6.12 kilowatt. This is the way NPMS, and this is the only way, the right way of designing it. No major balancing issue. Of course, you can say here the within a module there may be balancing. What if the cells are of not same voltage? Well, this is the reason the cells in parallel has to be carefully chosen. They are exactly similar kind. And while charging, discharging, you have to make sure that different current does not flow through. That is the reason you actually connect them like this. You have to make sure that the resistance is not difference. Now, if the resistance is different, different current will flow. So, don't worry about it. If internal resistance is different, you apply the same voltage, different current will flow. So, you have to worry about each and every of this. There is a self balancing, and at time you can enable some more balancing, which is okay, otherwise you will end up in trouble. So, basically cells to module and module to pack. So, multiple cells packed in parallel to form a module, cells selected so that they are same voltage balanced, cells connected with a metal bar that conducts electricity. So, their cells are put on a metal bar, so that there is enough, it does not give too much of resistance, it is conducts very easily. Multiple modules is put into a series to form a pack, and then there is a battery management system which will monitor the voltage of every module, the current of every module, and temperature of every module. And for lithium ion batteries, it will then try to work to get optimal performance. During charging, if unequal current flows between multiple batteries, you will try to do what is called equalization. It monitors voltages and temperature of each module. If a module is not getting sufficiently charged, you bypass another module or you let more current flow into that module. If temperature of any module is going up, slow down, do not let it charge. If a module is overcharged as opposed to another, it impacts life. And there is a two methods of balancing. I think probably Kaushal will cover that more. One is a passive balancing and another is a active balancing. Passive balancing basically means bleed one module with higher voltage through a resistor, so that some current flows into the next module. Active balancing stop charging a module of higher voltage and instead charge the other module with lower voltage. And then BMS has to worry all the time about temperature. A very important component of electrical design, as high currents are involved, a conductor is not a zero voltage drop. That is the point that I am making. Smallest resistance difference between two electrical paths may result into differential voltage drops. Current will flow from one rather than or another rather than the other, creating imbalances. So, a lot of imbalancing take place because electrical design is poor. In fact, a very interesting thing that I had come across, there are, let us say, there is a metal plate to which all the cells are connected. This is then connected in series to another metal plate where 4 more cells are connected. And these two metal plates can even be same, does not matter. You will think you have done it right, you have a thick metal plate to which you have connected. But look at this path from here to here is shorter path as opposed to from here to here. Shorter path will have a smaller resistance, longer path will have a longer resistance. Because there is only single connection between these two, you have a problem. So, the way to correct is that you will have multiple connections. You can't have a single connection. Then more or less same amount of current will flow. Oh, same thing I am showing here. Okay. If a current enters here and is supposed to be going here, yeah, if the current same thing, current is entering. If it goes through A, it encounters less resistance. It goes to D if your, let us say, inlet comes from one side. Inlet also has to come from a way by which all four gets equal. And this is the kind of problem that you will get into. It happens more between modules as current from one cell and module to another is more as compared to from another cell, more cell. A continuous imbalance deteriorates capacity. Some of that can be corrected, but a continuous imbalance can deteriorate capacity. So, electrical design has to be carefully done. I want to point out two more things and stop here. What if there are failures? What kind of failures happen? Suppose you have modules NP, n cells in parallel, m in series, and one of the n parallel cells become open circuit. If it is open circuit, suppose there are 4 of them, now only 3 cells are in parallel, one of them is not there. Okay? So, suddenly this is happening only in one module, other modules have full capacity, but this one module capacity has gone by 3/4 of the original one, overall pack capacity will go down by 3/4, because when the current flows, the current, if you try to flow more, if all of them are getting charged by 1 C, this will start getting charged by 1.33 C, that will destroy the pack completely. Overall capacity itself goes down, because though other cells have capacity, capacity will not be utilized. So, open circuit basically immediately means in any model one cell is all that one has to do. Suppose there is a short circuit, one of the n parallel cells, all the cells in parallel will get short circuit. So, your serial voltage will go down by 3.7 volt, which basically means the voltage has gone down, your motor etcetera, everything has been designed to operate at a certain voltage, now they will get differential voltage. But still short circuit is better than open circuit, open circuit hurts you much more. So, drivetrain will get poor performance, but one can do that, and these are to be monitored. The BMS has to monitor if anything like this has happened. Now, replacement will involve taking out the module, and these are all modules which are welded together, very difficult to take out the modules. So, replacement of module may be sometime possible, replacement of cell is not possible. Now, when you do the design itself, you have to worry about what will I do if I have to replace, how difficult will it be. You can't think about it later on. So, in the design time you can sort of say these things I will only connect through screws, so that they can be taken out. I will connect even the bus bar that I will connect through screws. So, I can open up the bus bar and take this out. If a serial connection between module fails, battery fails, it does not go through, but it is generally easier to repair. May require some bus bar replacement. What happens if a BMS fails? That is more easy to detect, and it does fail. BMS fails more often, but easy just to replace BMS, recalibrate everything. You have to worry about again SOC and all those kind of things. But the other problem that you often find, that you have to switch in current, switch off current, and for that you use MOSFETs. And MOSFET is a heat dissipating device. If a MOSFET is getting, and you are supposed to remove that heat, if a MOSFET is getting overheated, you will see the temperature. It is a design issue. If one MOSFET is getting heated compared to the others, you have to worry about it. You have to shut down that MOSFET, otherwise the MOSFET is likely to fail. Temperature sensor failure. There are lots of temperature sensors. Every module temperature is going to be sensed. Every MOSFET temperature is going to sense, and you find sometime these temperature sensors are not very good quality, in which case they will give you all kinds of results and you will end up doing something totally different from what you were supposed to do. Sometime the sensor will fail, sometime sensor will give you wrong temperature, and you have to detect it. Otherwise, these are dangerous, because it can result into meltdown. You think that there is nothing wrong in the sensor, but it is getting heated up. It is one of the most risky thing. Cell capacity deterioration, that is another thing that happens, and largely it is unbalanced cells in modules. Battery pack capacity deteriorates. Incorrect SOC and SOH estimation. One of the important thing, we had a battery with incorrect, and the drivers will complain saying, sir, it was showing 40% SOC, and suddenly my vehicle got cut off. For a long time we thought something was wrong in vehicle. Something was wrong in display. Actually, we found out later on it was SOC, SOH estimation mistake. It can result into a problem. So, to sum up, we have looked at a conceptual design of a battery pack so far. Not so carefully at what will be the mechanical design which will stop the bulging, the pressure, how will vibration be tackled. Not at thermal design, we have basically done electrical design, and we have not done the BMS design. This is what Dr. Kaushal will actually do in his set of lectures, get into a depth of each of these things. This is what a battery pack design will be. The simple configuration of putting them in series and parallel is fairly easy, everybody can do it. Electrical design is somewhat tough, but because you do not understand 200 amperes. If it was 1 ampere, the problem will not be so serious. A milliohm resistance will only give you a millivolt difference. So, electrical design we dealt with minimally, he may deal a little bit, but more carefully as mechanical, thermal and BMS design we will look at. Cell selection itself is critical in price and performance. Cost issue will be actually looked at very carefully in the next section. Cell performance in life cycles and impact of charging discharging rate, operation temperature, depth of discharge, all of these will have impact on life cycles. All of this will have impact on cells. That is the next section. We will look at what is the battery cost, usage cost that I have been talking about right from there. The pack design also impacts the battery life. Cell imbalance has highest impact on battery life. Pressure on cells, vibration, cell temperature differentials, differential currents impact life cycles of the battery. Inaccurate determination of SOC and SOH of course hurts the vehicle performance. After some time starts hurting the battery performance. So, this is what we have to summarize this, and what we will do next is there are some questions, fairly simple questions. I will not go through the questions. Well, let me quickly look at it. Battery pack of 115 kilowatt hour with a nominal voltage of 350 volt. Cells are 3.65 14Ah. Configure what will the battery voltage at 0% and 100%. Need a 0.5 kilowatt hour battery of 48 volt. What are the cells that I will use? What would be the configuration? A battery pack of 375 volt 200 ampere hour is to be made to power a luxury car. One battery pack is made with 3.65 volt 4Ah 21,700 single cell, another with prismatic cell. Suggest NPM mesh configuration for each case. Find the total number of cells in each cases. A cell involved module of n parallel cell fails. Find the resultant nominal pack voltage in V and ampere hour for both the packs. You will find some interesting results. A battery pack of 2P 14S is made using 13Ah lithium ion cells to power a two-wheeler. The pack is used in the field for some time and has undergone 5% degradation. So, SOH is 95%. The pack operation is limited between 10% to 90% SOC. Indicate the SOH percentage of this battery pack and DOD of operation, depth of discharge of operation. I have already given you the answer. What is the nominal voltage of the pack and the capacity in kilowatt hour? What is the usable capacity of the battery pack at the current level of SOH? And there are various true and false. Please answer that, and you will then come to the next section, which I will do next class.